All right, let's begin our next lesson where we're going to start to look at the translations of sinusoidal functions. So over the next couple lessons, we're going to be moving our sinusoidal function around our Cartesian plane, as well as changing the shape of it a little by stretching it or compressing it or reflecting it across an axis. Okay, but we're going to start off easy and just start with translations of sinusoidal functions. If we look at our learning goals, we're going to explore the effects of d and c for the function y equals sine times x minus d plus c. So far all we know is y equals sine x, y equals cos x. And what you're seeing now is that there's these other variables d and c. All right, so we're going to explore the effects that those have on our base function of y equals sine x and y equals cos x. We're going to graph the equations in those forms by using a table of values. So I'm going to show you how to do that. And then from that we'll also look at determining key properties of those graphs. Things like the period, the amplitude, the domain range, phase shift, and vertical shift. All right, we're going to use Desmos in this lesson. So we'll get to that in a second. But first, let's recap. What does the graph of y equals sine x look like? I want us to remember our table of values here. We're going to need to remember this. So remember that the x's go by 90s. Okay, we did this in the last lesson. And then our y's, it starts at 0, goes up to 1, back to 0, down to -1, and then back to 0, the starting point again. So if we call this 1 and -1 there, we go ahead and we plot this, and we have one cycle of the sine function. The cosine function, if we remember, is the same x values, okay, but the y values, the outputs, were a little bit different. Okay, so instead of starting at the equation of axis here, like in the sine function, we actually start at the maximum, so at 0, 1, for the cosine function. Okay, there's our first x-intercept. Then at 180, we're at -1, and then back up again. So one full cycle of the cos function looks like this. Noting that, again, it starts at the max here, whereas the sine function is the exact same, except it starts at the EOA, the equation of axis. Oh, forgot to fill this in. Okay, let's move on and let's take a look at our investigation here. So we're going to use Desmos, and the first thing we're going to do is we're going to change the window settings here. So we're going to click on the wrench icon and change our x-axis units to go from -360 to 360, and my y's to go from -5 to 5. Okay, then we're going to plot these three functions on the left of the screen. So let's go into Desmos. Let's hit the gear, change from -360 to +360 on the x-axis, and -5 to +5 on the y-axis. All right, and then we're going to plot y equals sine x By the way, sine is found in the functions button there. Oh, and my mistake, actually, the one thing I forgot to change. Right now we're in radians. We need to change it to degrees. Okay, so let Desmos know that we're in degrees on the x-axis there. Okay, and there's y equals sine x. Looks pretty good. And this makes perfect sense of what I expect. I expect one full cycle from 0 degrees to 360, which is right there. Okay, one full cycle of the sine curve. There it is. Okay, then we're going to do y equals, press functions, sine x minus 30. Okay, and then lastly, we can close that bracket there. Lastly, let's do y equals x plus 60. Okay, so here we have our three graphs. Okay, we got the red, the blue, and the green. And what I'm going to do is I am going to choose a maximum point on my y equals sine x curve. Okay, and just to outline where that maximum point is, because now we're gonna observe the effect that this x minus 30, x plus 60 had on our graph. Okay, and let's take it step by step. Let's go to the instructions. How do the graphs of y equals sine x and y equals sine x minus 30 compare? Okay, let's take a look. So let's hide this green graph here. And let's just look at our first two graphs, our red and our blue graph. Let's see what happened. So we went from a maximum, we're picking a point here. We went from a maximum of 90 and 1. And what happened to that maximum? It now moved and is at 120 and 1. So it was at 90 and 1, and now it's at 120 and 1. So what would you say happened here? Would you say something along the lines that because we went from 90 to 120 on the x-axis, and it's clear that this is clearly shifting to the right, and it's shifting to the right 30 degrees. Okay, 30 degrees. So when it says x minus 30, it's actually shifting, the graph shifted to the right. So the graph of y equals sine times x minus 30 shifted to the right 30 degrees. Let's look at the graphs of y equals sine x and y equals sine x plus 60. So this time I'm going to unhide my green graph, hide my red graph, and now we have 30, I'm sorry about that. There you go. Okay, so now we have, this is my original y equals sine x graph, my red graph. My coordinate for my maximum there is 90 and 1. Okay? My new maximum on my green graph is 30 and 1. So I went from 90 to 30. What happened here on my x-axis? I translated this time to the left 60 degrees. 90 minus 30 is 60. Okay? So the graph of y equals sine times x plus 60 translated, you can use the word translated or shift, translated to the left 60 degrees. Now you might wonder, like, how could, if it says x plus 60, why did it shift to the left towards the negative end, right? Why does it do that? Well, the general form of the equation is this. Okay, this is the equation we're working with. And actually, currently we haven't done anything with C, so I'll just leave that out. So what happens is, if you're going to the left 60 degrees, that means D is equal to negative 60, right? So when you sub in negative 60 for D here, look what happens. You get a double negative, right? And a double negative becomes plus. And that's why when you see an x plus 60, it really means that D was negative 60 and you're going to the left 60 units. Okay, so here, if d is greater than 0, the graph is blank, and if d is less than 0, the graph is blank. And actually, before we get to that, sorry, our conclusion, if y equals sine times x minus d, then the graph of y equals sine x is shifted or translated left or right d units. Okay, and if d is greater than 0, the graph, so if d is greater than 0, so if your actual d value is greater than 0, that means you're shifting to the right. Okay, but in your equation, you know that that will look like x minus 60, but that just means that your actual d value that you subbed in must have been a positive 60. And if your d is less than 0, so it's negative like in this situation, you're actually shifting left. Okay, so you can use the term translated. I'll be pretty flexible with what you use here. Translated, you can use shift. You can use, and actually the most proper term is phase shift. Okay, because you're dealing with angles, it's called a phase shift. But now let's look at the difference here. Here, our sine x minus 30 was in brackets, right? X plus 60 in brackets. But look down here. Here, the x is by itself, and there's nothing beside it, because there's no brackets, right? And so it's just cos x plus 2 on the outside, okay? And so what we're looking at here is the effect of this variable here, our c value. We've already now looked at what d does. It translates or shifts our graph left or right. Now we're going to look at what c does. So we're going to plot these three equations, and all plus 2 minus 4, that's our c value there. Okay, it is not our d because it's not in the brackets. So let's plot these three curves, and then we'll investigate them just like we did above. Okay, let's start off with y equals cosine of x. Then we'll do y equals cosine of, oh, no brackets there actually, cos of x. And then it was minus 2. And then y equals plus 4. Okay, so I think this will be fairly obvious to you. Here's our original, okay, our original max value. Let's hide our red equation there. By subtracting 2 at the end of our equation, what ended up happening? We took our max value of 0, 1, and where did it go down to? Negative 1. It went down 2 units. So when you have a minus 2 outside of the brackets, you are going down 2 units. No tricks there. There's no opposite sides. There's nothing. Why is there no opposite, taking the opposite sign? Because the actual general form of the equation doesn't have a minus sign like here. It actually has a plus sign, in which case there's no kind of little double negatives that would end up happening. Okay, so whatever you see is what you get. Okay, sorry, and they asked us to graph plus 2, but that's okay. How do the graphs of y equals cos x and y equals cos x plus 2 compare? The graph of y equals cos x plus 2 is shifted 2 units up. Okay, and how do the graphs of y equals cos x and y equals cos x minus 4 compare? Well, it shifted 4 units down. is shifted 4 units down. Okay? So, in conclusion, if y equals cos x plus c, then the graph of y equals cos x is shifted up or down c units. Okay, no tricks there. There will be no double negative situation. Just if it's a minus c, then it's down. If it's a plus c, then it's going up. So if c is greater than 0, the graph is shifted up. And if it's less than 0, it is shifted down. So in closing, D represents the horizontal translation, so it moves our graph left or right, whereas C represents the vertical translation up or down. Okay, so one affects the x values, the other affects the y values up and down. Okay, let's do a straightforward question here. Y equals cos times the x times x plus 180, and it says state the translation on each function. So what is happening to my original function y equals cos x here? What is happening? There is a horizontal translation or a phase shift. I don't care which terms you use here. Phase shift 180 degrees to the left or right. If it's plus 180, that means we subbed in a negative 180 to get plus, because it's in the brackets. So it's left. Here, the plus 2 is not in brackets, so that must be our C value. Therefore, there is a vertical translation 2 units up. Okay, and here we have 2 different translations. We have a phase shift 45 degrees to the right, because it says minus 45. So we're going to go, we know that D must be positive 45, and C is negative 1. So vertical translation 1 unit down. Okay, so straightforward. Now, let's look at how to sketch this. Okay, how to sketch the graphs of these equations. We're going to sketch both. In this case, we're going to sketch y equals sine x as well. And in this case, we'll also sketch y equals cos x. So we'll have 2 graphs on each, just so you can observe the differences. Okay, so let's start with the table of values of y equals sine x. Okay, we're going to plot that first. Start at 0, 90, 180, 270, and 360, right? And then y equals sine x, we know that it starts at the EOA, it starts at 0, goes up to 1, back down to 0, down to negative 1, back up to 0. So you get something like this. Let's call this 1 and negative 1. Okay, there's y equals sine x, but now we're going to observe and learn how to graph and include this x minus 45. And here's all you do. I told you earlier that 45, that when it's in the brackets like that and it's our D value, that to get minus 45, you must have a positive 45 for one thing. So what's happening is that you're translating all the points to the right 45 units. Well, if you're translating the points to the right, that means you're affecting the x values only. So only your x coordinates will change. So what you're going to do here in this table of values is you're going to take now all your x's and you are going to add 45 to them. So you're going to take all of these and add 45. And that's going to move everything to the right 45 units. So 0 plus 45 is 45. 90 plus 45 is 135. 180 plus 45 is 225. 270 plus 45 is 315. And then 360 plus 45 okay, we're actually going to have to change our scale, is 405. Sorry, I'm just looking up here, and we're going to have to change our scale up, actually. And so what I'm going to have to do, the scale's not going to work, because we have to go up to 405 here, and that's okay. We can fix that easily. Let's go back. Okay, and let's change, instead of skipping all the way to the third line to get 90, let's only skip 2 lines. So let's go 90 here, okay, 180 here. Here you're going to have your 270. Here you're going to have your 360. Here you'll have your 450. Okay, and we can stop there. Okay, so I changed the scale up a little bit. Okay, now we are going to plot our new, well, let's plot our original sine x, y equals sine x, no problem. Here's your original y equals sine x, right? Okay, so now we have new x values. Did anything happen to our y's? Did we add or subtract anything to our y's? No. So they're actually going to stay the same, which makes sense. There's no c value in this equation. There's only a d value. So we're going to plot now our new points right there. So 45 and 0. I'll do it in a different color. 45 and 0 right here. 135 and 1. 135 and 1. Okay, so if this is 90, that's 180. Halfway right there. Sorry, and I shouldn't draw that there. Right there. So essentially everything's just going to move over one grid mark here, right? Our next point is 225 and 0, which is right there. Our next point is 315 and -1, which is right there. And our next point is 405 and 0. And so you can see we have just plotted our second curve, which is identical to the first. The only difference is we moved it to the right 45 degrees, which means we added 45 to only my x values. My y values stayed the same. Okay, so we added 45 to all my original x values. Okay, this one has both a d and a c value. So our d value here must be -30 in order for us to have gotten a +30. My c value is just -3. So I know I'm going to be moving to the left 30 degrees and moving my graph down 3 units. But how do we show that as a table? Okay, so now we're doing y equals cos x, right? Put in your original function. Okay, and for y equals cos x, remember you start at the maximum. Okay, so the graph looks, and we are going to keep this scale. The only thing is I may have to add a grid mark on the side here, and my apologies, this is my mistake. May have to add just a, maybe I'll do it in a different. Okay, it's not going to look great, but that's okay. So let's plot our original function, 0 and 1. Let's call this 1. Let's call this -1. Oh, and actually, no, we can't do that. We can't skip a line because now we're going to be moving down 3 units. So no, that's actually not going to be proper. Because we're moving down 3 units, I can't have this be +1, right? I can't, because I've got to go all the way to potentially 4, or sorry, down below -1. I'm going to have to go down to -4. So I'm going to have to keep the scale which is currently there, which is just going by 1s. Okay, so let's graph our original function, and each grid mark will just be 1. Okay, there's my original function. 1 cycle of it, where this is 1, 2, 3, 4. This is -1, -2, -3, and -4. Okay, now we are going to take this original function. We know that we're moving to the left 30 degrees, which means we're going to take all my x values and subtract 30. Okay? Fill it all in. Okay, so I have my new x coordinates for my new curve. I'm moving everything to the left 30 units. I'm subtracting 30 from all my x's. But now, I'm also moving the graph down 3 units, right? C is -3. So I'm going to take all my y's, because y deals with the vertical, all my original y's, and I'm going to subtract 3 from them. So I get 1 minus 3 is -2. 0 minus 3 is -3. -1 minus 3 is -4. And then back to 0 minus 3 is -3. And 1 minus 3 back to -2. So now I'm plotting this new curve here where we moved the x's to the left 30 and we moved the y's down 3. So here we go. I've got -30 degrees. I should say -30 degrees and -2. Let's call this -30. That's why I drew my extra grid mark here. So -30 and -2. Let's put it down there. Okay. That's why I drew this extra grid mark. Okay. I know it's a little sloppy there, but it's good enough. It'll get the job done. 60, -3. 60 degrees, if that's 30 60s right here, -3. 150, -4. Okay. 150, -4. 150, -4 right there. There's 150. Going by 30s. 240, -3. 240 back up to -3, and then 330, -2. And there you have it. There's our curve that's been moved to the left 30 units and moved down 3 units. Okay, and we did it using a table of values. By the way, just want to mention, where is my new equation of axis for this curve? Take a look. It's at -3. Do you think there's a connection between the fact that this being -3 and my new equation of axis being at -3? Do you think that's just that just happened by chance, or do you think that that is something that is true for all equations? Well, here's how I'm going to show it to you. What is the value here? What's the C value here? 0. And what's my equation of axis going through? 0. And here it was -3. And look at this, my EOA, that middle line, that average line, is going through -3. So make a little note that the EOA is equal to your C. Okay? All right, let's do one last problem. The function of y equals cos x is transformed so that it has a phase shift right 67 degrees and a vertical shift up 5. Write the equation of this transformed function. No problem, right? So now we're just going backwards. So let's write out the general. You always want to write out the general form here. Oh, and it's cos. So the general form looks like this. This will avoid you making a mistake with D. Because now we're moving to the right 67, which means D is positive 67, and we're going up 5. So C is positive 5. And now all you do is you come here, you put your minus, right? And now you're doing minus a positive 67. Minus and a positive side by side, the minus wins. So it's just minus 67 plus 5. But be careful here for the double negative. Like if this was to the left 67, then you would be plugging in a negative 67, which would then give you a double negative situation where you have to add 67. Okay, and that concludes the transformations using D and C for our sine and cosine functions.